Okay, anyway, so we're going to start with the first case. The first case was you have a proton and you have an electron. Now, why is this case different from the other one? Not that much different, but it is different in two different respects. First of all, the proton and the electron attract. So attraction is going to be one sign. Repulsion will be a different sign. I will try to figure out which sign. The formula tells you, but it also has to make sense. Otherwise, forget it. Okay, so I'll tell you why that sign makes sense. The reason why the second case is different is because the proton and the electron have very different masses. So in that case, you can use one approximation. But when you have two protons, then both, if you release them both, then obviously both are going to start moving. You can't keep one constant. They both have the same mass. So normally what happens is in actual metals and things like this is the electrons that are moving because the other charges have much more mass, so the acceleration is much less, so they don't move that much compared to the electron. So that's what we're going to start out by assuming. Okay, so we have a proton, we take the electron is very far away, and then we just release the electron and then see what happens. Well, what happens is they're attracted to each other. Okay, so what is the sign? So again, it's always the same thing, it's conservation of energy. We discussed this already. E initial equals E final. That's how student wrote it. I'm going to keep the student's notation. That's my notation. Okay, so conservation of energy. So you have the initial. So initially, the electron is very far away. So you have potential energy and you have kinetic energy. Okay, to consider. Now, when it's very far away, I'm going to say that I have the electron. I just let it go. Right when it's very far distance, I let it go. So initially, the kinetic energy is 0. So we have kinetic energy of 0 initial. And then you say potential energy. Well, here is the potential. It goes like 1 over r. As r is very, very large, we said that last time for gravity is the same thing here. When r is very large, you must put 0 because that's a very large number. Now, these two things are attractive, right? So therefore, you can think of it that way, and you'll see it has to make sense. Or you can use the formula and say, okay, one of these charges is positive, the other one is negative, but they have the same value, right? So I can also write this as k q squared because they have the same value. But one was positive, one was negative. That's that minus sign there. I already put in the minus sign. The q squared cannot be negative because it's q squared. It's the same for both particles, the same charge. Okay, so this thing is a positive, but since it's one positive, one negative, the term is negative. Okay, and then you divide it by r. So therefore, I'm going to use this formula up here. So the kinetic plus the potential initial equals the kinetic plus the potential final. Okay, great. So notice the initial potential is 0 because they're very far apart. The final potential, what is that? Well, I mean, are they going to hit each other? That depends on what the final radius is. Let's say the final location is the proton ends up at some distance r0 from the electron. And let's call that r0, whatever it is. They have to tell you that. You know, if you say, you know, actually, you know why you might think you should put the radius of the proton in there. The reason why you really shouldn't do that is because if you did that, solve that problem, then the electron, by the time it hits the proton, would be moving at relativistic speeds, and then you wouldn't be using the right formulas to solve that problem. So you wouldn't want to choose the size of the proton for that reason. But anyway, that's a technicality. It doesn't matter. They end up some distance separated, but from each other. So you're going to have minus k q squared over r0, and you're asking what is the speed of the electron. One is, well, the electron is the only thing moving here because it's the thing that's light. Okay, so then you just have 1/2 mv electron squared. The proton, you can consider, the assumption is that you're saying the proton is so massive compared to the electron, the proton doesn't move. That's like saying the sun is so massive, it's kind of like the same ratio. The sun is so massive that the sun doesn't move, it's only the earth that moves. Okay, it's kind of like the same ratio of masses. Okay, right. So you can see, okay, I'm almost done. I mean, I want to go fast from here on out because we have a bunch of stuff to do. But you can see already that the signs worked out fine. The reason why they worked out fine is these two guys are attracting. The electron is gaining kinetic energy. So if you think about it, you should always in your head, if the kinetic energy is increasing, so if I say this, change in kinetic energy is positive, then the change in potential energy must be negative. That's conservation of energy. That's so simple, right? So if the kinetic energy of the thing is increasing, then the potential energy of the thing must be decreasing. Well, if you start out at 0, how do you decrease it? The only way to decrease it is to make it negative. So you absolutely need that negative sign in there. Otherwise, it doesn't make any sense. When they're separated very far, the potential is 0. When they get closer, the potential must be less than 0, so negative. So that's why that minus sign is totally needed. Okay, hopefully you agree with that minus sign. Since I have that minus sign, I don't have any problem solving for the velocity of the electron. I move that to the other side and I put the R0 and that's it. Okay, so that gives me the velocity of the electron. Now, very quickly, let me contrast that with a second example, just to make sure we agree on the signs and also what is the difference in this other setup. Okay, now instead of proton electron, which is attractive and has a negative sign in the potential, now I'm going to do 2 protons. Now there is no negative sign in the potential. I use the same formula every time. K, Q1, well, Q1, Q2 are the same. They're both positive, so that's that. There is no negative sign now, right? There are 2 positive charges, and we're using the same formula. Here is the formula. Okay. So now the question is, they start out separated some distance away, and I want to know the final speed of the protons. Can somebody, instead of me saying it, this is slightly different from the other one. How would you write energy conservation in this case? Can somebody do it? I mean, it's not, can somebody do that instead of, what would be this is conservation of energy for a proton and electron? What would be conservation of energy when you have 2 protons and you release both of them? You let them both go. How would I do conservation of energy then? Somebody want to put the formula in there, or how would that go? So initially the kinetic energy is 0. Okay, I'll get you started. See what you, okay? So I put 0, right? So that's 0 kinetic energy. The protons are not moving. Now you let them go. Now they're going to separate and go off to infinity. And you're asking, what is the speed of the protons at infinity? So the initial potential energy is K, Q squared over R0, which is the initial separation of the protons. So initial kinetic, okay. So what I want to know is the final kinetic energy of the protons. And the final potential energy is 0. Now, there is something wrong with this equation. I'll ask it a different way instead of asking you to write it. There's something wrong with this equation. What's wrong with this equation? Is there something wrong? I mean, you already know there's something wrong since I wouldn't ask it otherwise. But what's wrong? In this situation where I let, right. So that you see looks almost the same. But the difference is here you assume the electron was the only one moving and you said, oh, the mass of the electron is so little compared to the mass of the proton. And it is very little. I think, I don't know, it was like 1,000, 1,000, something like that. So it's very small compared to the, okay. So that's why you were able to only use the kinetic energy of the electron. But here, of course, you can't assume one of, well, you could, the problem could say, oh, somehow or other, you put a finger on the proton and you don't let it move, you pin it, and only one moves. Well, that would be only one term. But in general, of course, you would have the potential energy and then you have 2 kinetic terms. That's where the energy goes. So because you have the 2 protons and they have the same mass. Actually, there are a couple of problems that are a little bit challenging in the Master in Physics for next week on this. I'll try to give you help with that because otherwise they're gonna be challenging. So the next week, Master in Physics, I would like to definitely help you out. So I'll try hard to do that, find a way to do that. Yes, we'll have time. I'll find a way to do that, yes. There was a couple of problems in there that will be challenging if I don't say anything. There is conservation of energy, but you also sometimes have to worry about conservation of momentum. And you probably did that in Physics 50. We're not going to cover that in great detail, but there is one problem in Master in Physics that asks you to do both conservation of energy and conservation of momentum. I will help you with that problem. Okay. Back to the PowerPoint. I'm going a little fast again. Please, if you have questions, let me know. What I just went over will show up in the V-final. Sorry, Jason. You still have the question, or maybe I covered it. I'm not sure what the question is. You want to speak or? Oh, okay.
Professor?
Yeah.
What was wrong with the previous equation again?
Right. Okay. Yeah. So that's what Emma said. It's not that it's wrong. Is that when you, right, if you don't, so in this case, the second case, right, so it's what Karen is saying is what's wrong. You have to, if you let both protons go, they will both start moving. So you cannot just consider the kinetic energy of one of the protons. So when I wrote it originally, I wrote the kinetic energy initially 0 for both, so it's 0. The potential energy is what I wrote. And then it's equal to the kinetic energy, but I only had one kinetic energy term. But actually you need two kinetic energy terms, one for each proton. So what you need the formula to be is without the 1/2. You need to get rid of the 1/2 because it's 2, 1/2 plus 1/2.
Oh, okay.
Right? So now it's correct.
All right, thanks.
Sure, no problem. Okay. Okay, so yeah, this is not, but again, notice where I'm using this formula. Please don't use it in some other, this happens all the time in exams. You get flustered because the time constraint on this, and you forgot something, some piece, and then you start using the formulas you think you know, and you're applying them in places that you can't do anything with the formula. So if you use this formula, I'm giving you plates, and you're using this formula, what is this formula doing for you? Absolutely nothing. This formula only applies when you have point charges, a bunch of point charges, and they're affecting each other. That's it. Okay? Now here they're explaining what I just said again. When is it positive, when it is negative, when it's attractive, when it's repulsive. This is the key thing. You can remember this. This graph here is when the charges are negative of each other. So one positive, one negative. And the point here is when the charges are separated, the potential energy is 0. And then since it's 0 separated, everything else has to be less than, and so everything has to be negative. So that's what they're trying to tell you. When you go to infinity, you go to 0. But when they get closer, then you have minus. So in the case we were doing, it would be kq squared over r with a minus. So at infinity, this is 0. And everywhere else, this is negative. It has to be less than 0. So when you have a positive and a negative, or a negative and a positive, makes no difference. Then the highest the potential energy can be is 0. If you're using this formula, that's true. That's the greatest potential energy you can have is 0. Okay, everything else is negative. Okay, I did go over that, but just please keep it in mind that there is that sign issue. If you put the wrong sign, now all of a sudden the electron is going to slow down. Well, that doesn't make sense. Okay, now here they're just trying to tell you if you have a bunch of charges and you want to calculate the total potential energy, the nice thing about this is that you do not have to worry about the vectors at any point. So if I want to calculate the total potential energy of charge Q0 due to the presence of charges Q1, Q2, Q3, then it's just a straight up addition of these three things, these three terms. And there's no vectors, there's nothing to worry about. So it's kind of easy. You just keep adding the potential due to one of the charges, the potential due to the other of the charges, the other charge. So it's really not, so that's why this is nice. Not worrying about vectors is kind of nice. However, you do have to worry about the signs. Okay, so some of these terms could be positive or negative, depending on whether these charges are positive or negative. So in every case, you just use the formula KQ, Q1, Q2 over R. That's the formula. Okay, so if this charge is negative, then that term is negative, and so on. Okay, so that's the only thing. You got to worry about the distances to the charge, and then the sign of the charge. Of course, the sign does matter. Okay, but that's it. No vectors. So if I ask you to do this in the exam, that's a good news, because that means it's a lot easier. Okay, you probably know that, but just making sure. Now things get confusing. Confusing but used all the time. I'm sure you're doing labs. You probably already talk about potentials. So they probably don't get into the definition, but the definition, you see what they did. They just took out one of the charges. So it's kind of like, let me just remind you, when we did force, that's a vector. But the definition was just Q, whatever the Q you're talking about, and then the electric field at the location of that Q. So if I want to know the force on a charge, then I figure out the electric field at that location where the charge is located, then I multiply by the charge, and that gives me the force. So that was the definition, the connection between forces and electric fields. And the force always points in the direction of the electric field, so that's kind of easy. But it was just a definition that seemingly we didn't need, but later on turns out to be very useful. So that was true. So now that we're doing a very similar thing, we're doing U, as in potential energy, and then we're going to say Q, and then times potential. So that's pretty simple, but confusing at the same time, because this could have positive or negative charge. So therefore, the potential energy and the potential don't have to have the same charge, the same sign. So that is confusing sometimes. Okay, so voltage is potential. Okay. If you want to calculate the potential due to a bunch of charges, then you do the same thing, but you just you only need one charge, not two charges to do that. Okay. Now it turns out, instead of giving it abstractly, there's a connection between, instead of giving it abstractly, let me give you a practical example. It comes a little later. There's always a connection between the electric field and the potential. And I already showed you the formula. It's at the last PowerPoint slide here has this formula, and this is just the inverse of that formula. It's the integral form instead of the derivative form of the formula, but it's the same formula. So at the end, the formula is written like this. And I want to show you that works. We're not going to use this a lot, but I want to show you how that works. So the electric field is minus the gradient of the potential. That's the formula at the end. Let me show you just very quickly. I already showed you, but let me show you again. Now, notice, okay, actually, this is better than the formula I just wrote because I forgot the arrow part. Now, notice what happens here. This is kind of important. This is a scalar. It's not a vector. Just like the potential energy is not a vector, the potential is not a vector. So you might wonder, how the hell do you get a vector out of it then if the scalar is not a vector? Well, it turns out that when you take a gradient, you can turn a scalar into a vector. Okay, so that's what they're telling you here. If I have the scalar potential, if I take a derivative with respect to x, then I get the x component of the electric field. So the electric field is a vector because it has three components: Ex, Ey, Ez. So those are the three components of the electric field. If I want to get each one of them, then I take different derivatives of the same quantity, the potential. Okay, so this is in general true. Let me show you an example of this. Okay, so instead of this is kind of like a calculus general point. It's of course very useful, but instead of just keeping it at this general level, let's do an example to show that yeah, the potential, the relation between potential and electric field. Okay. They have it up here. I wanna spend a little bit of time. This is more practical, and we've discussed this a little bit, and then so it will be possible for us to see how the relation goes. And people like to ask. I may include a multiple choice question about this. These kinds of questions show up a lot. It's like almost like a true and false thing. Like if the potential is this, the electric field has to be such. Actually, I'll give you some practice problems like that at some point, probably next Monday. Some practice questions like this. But at this point, let's just see a specific example and see how the electric field and the potential relate to each other. Okay, and show that, yeah, that formula, that works, at least for this case, but it's in general. Okay, so we did cover this case. This is a conductor. Okay, so in a conductor, we agreed that the electric field inside the conductor is zero, always. Okay, so because if there is not zero, then the charges will move. So when you have a quasi-static static situation, electrostatics, then the electric field inside the conductor must be zero. Okay, so that's what they're telling you here. If I do a plot of the electric field inside the conductor, electric field is zero. Now, right outside the conductor, I also told you that how to calculate that. You use Gauss's law. When you're outside, if you make a Gauss's volume, you're enclosing all the charge. So that's all the charge. So outside the conductor, it goes like that. And right at this point, it goes from zero, it jumps because there is a layer of charges. So right inside is zero, right outside it jumps. So that's kind of funny behavior. That's telling you you're concentrating all the charges right at the surface. That's why it jumps. Okay, so this is how I would go for the electric field. The electric field inside is zero, outside is like 1 over r squared. Okay, great. Now, how about the potential? So remember, in the end, I'm going to be able to use this if I want to, with a minus sign. It needs that minus sign in there. So just for this particular situation, let's think about, I'm not going to ask for this in general. You know, it's calculus. Of course, you can do this in general for whatever you want. But let's just worry about if I take the derivative with respect to radius of whatever is here. Do I get the thing above? That's the question. So if I take derivative with respect to radius of 1 over radius, what do I get? Well, actually, this is minus 1 over r squared, the derivative of 1 over r. I'm not talking about the integral. The integral is the log. But this is the derivative of 1 over r, is minus 1 over r. So when I take the derivative of this quantity here, of course, I'm going to get this quantity here. And you might say, where did the minus go? Well, there is this minus from taking the derivative of 1 over r. That has a minus in it. But there is that minus as well. So there is no inconsistency. This is correct. Okay? How about inside? Okay, here is the last important point of this. The potential inside the potential inside the sphere doesn't have to be zero. It just has to be constant. Because if I take the derivative with respect to radius of some constant value, that gives me zero. Okay? So again, the electric field and the potential are not the same thing. They're connected by a derivative. Okay? This is not a major point of the exam, but you know, it is kind of important that whenever you have the potential, of course, you can recover the electric field from that just by taking a derivative. But you do have to put a minus sign in there. Okay, so the point is, if you take these two things, then you take a derivative, you will get this, and also you get that by doing this expression like that. Okay, I'm pretty much what I think about at this point. I still have a little bit of time, which is good, because I want to go to the problem in the exam. I want to be specific to that. Do you have any questions that something strikes you not quite clear on what I said? I want to go right to the question that I'm guaranteeing will be in the exam, so we can spend the rest of the class thinking about that. Okay, you want to do that? Let's do that. If I don't get any questions, I'm going to move right to that. Okay, so here's the question in the exam. And please, again, I'm talking a little too much. I would rather, we've already kind of done this a little bit. So let me remind you how this goes a little bit, but I'm going to ask a slightly different question than the one we asked last time. So this time it's similar, it's very similar, but we have a positive plate. I would like to use energy conservation. So let me tell you that the potential, and I'm going to leave the sign uncertain. I'm going to ask you to try to figure out the sign for the potential. Okay, instead of me telling you, and then we'll see the physics. Again, we'll argue it with physics. So I'm going to give you up to a sign, the potential energy of an electron in a plate is given by Q of the electron times E times how high above the plate is, and let's call that Y. So let's make that 0, you know, the plate, and then so what I'm going to do is I'm going to get an electron, I'm going to shoot it at some angle, and my question will be how high. So there's a positive plate, this is an electron. My question is how high will it climb? Okay, so how high, what is the maximum elevation of that electron, H? How high does it go before it turns around, starts coming back down? Okay, and the potential in this situation goes like Q, the charge, times the electric field, and the electric field is sigma over 2 epsilon naught, and then times Y, where Y is the elevation, how high? The Y-axis. Okay, so the question is, and then we're going to solve this two ways, and please let's try to get all the signs, everything correct, everything I'll spell out, I have it in front of me, in fact, so to make sure I don't make any sign mistakes for you along the way. And also I solve for the thing that I'm asking for, so that you can see that even if whatever way you do it, you get the same thing, of course. But the question again is, what is H? Okay, so please pretend that this is the exam. I think that's the most useful thing we can do right now. Instead of me just talking and talking and talking, pretend this is the exam and you have to know it already. So you're going to have a potential that goes like this. You have a kinetic energy initial. Okay, so you can define some angle here, theta, which could be whatever. I mean, let's make it 45 to be like super specific, 45 degrees. So you shoot the electron at some initial speed at 45-degree angle, and then you want to know how high will it go. Okay, so let's solve it together by conservation of energy first. Okay, and then I'll show you that you get the same thing by conservation, by using the kinematic equations like we did last time, but the question is slightly different. Okay, so what would the so give it a try, okay, instead of me saying everything. What should the equation be? Write the equation, the conservation of energy equation for me, if you don't mind. I'll give you like 5 minutes. I'll go get coffee. I'll come back. I have it in front of me, so, you know, I know what it should look like. So just write down what you think it should look like. And then I'll come back and see who got it right or what was the problem. Again, please, let's try to figure this out today instead of the exam. Makes a lot of sense. I'll be right back. I'm going to get some coffee. Right. Okay. Let's see. Emma has an option for us. Okay. Now, Emma, of what you have, what you wrote, let's think about this a little bit more. But yeah, I mean, it's conservation of energy. So you're going to write something like that. But let's think about your formula. Your formula says the initial speed, then there's the final, and then there's QEH. Now I asked for H, so H was an unknown. So V final, if that's also unknown, then you have two unknowns in one equation. So you couldn't solve for H without knowing VF. Oh, okay, right. I mean, there's nothing wrong with your formula. I couldn't possibly VF, right? Now, what is VF? So again, this is the condition at which the thing reaches the top, right? You're going to the highest possible. So Trent says VF equals 0. Okay, so you're saying at the top, the electron is not moving. Is that true? Only in the y direction. So it's only moving. Okay, but again, we're going to get to the bottom of this. But instead of me doing it, I want you to think of it right now. So you see what would happen if I gave you the exam right now. There would be some confusion. You wouldn't know exactly. So that's the issue. The issue is if you try to figure out things at the time of the exam, it takes too long. So you gotta practice them ahead of time. Mariana said is not moving at the top. Isaiah says only. So Isaiah, are you saying only in the y direction is moving, or only in the y direction it is not moving at the top? Somebody just write down clearly what is the condition of the speed at the top. Only in the y direction it is not moving. Okay, so what is the condition at the top then? Supposing that what you're saying is correct. So you will write Vx equals what? Vy equals what? According to you. So what is Vx then? Okay, so according to Isaias, Vy would be 0. How about Vx? Okay, well, if you put Vx equals V final, you still don't know V final or Vx. Do you agree with that, Emma? Remember, right, so what does that equal? Okay, we're getting there, Right, there you go. Okay? Okay, so we got there. You can only have one unknown. You can't have two unknowns, and you cannot do anything with the formula. So the key thing, there's always some key thing that you have to figure out. The conservation of energy is conservation of energy, but you gotta put the right signs and figure out what is the condition that you're solving for. So we did a little bit of that last time. Now you guys you got it. So the condition has to say that the top gets reached, exactly as you said, when Vy equals 0. At the top, there is no Vy, because if Vy is positive, then it would keep going up. If Vy is negative, then it would be moving down. No, right at the top is not moving up or down, it's just moving horizontally. at that point. That's the condition. That's how you decide that it's reached the top when Vy equals 0. So the only thing you have at the top is right. So the only thing you have at the top is the Vx. Okay? Okay. So Vy at the top is 0. Vx is constant always. It doesn't change. There's no acceleration in the x direction. So Vx is always the same thing. It's V0, whatever the initial is, 3 meters per second, whatever you give it initially, times cosine of 45 degrees in this case. Cosine of 45 is square root of 2 over 2. Okay? So let's now we're ready to solve, to put it in a form, in a conservation of energy form. But I hope you, my intention is to have this debate or this discussion, just to show you that there's always a little thing that stops you from getting it right away. So that easily, if you don't practice, that's what will happen in the exam with this question probably. Even though we've already done a little bit of it, you still have to practice it a little more. You don't want to get in the exam under pressure, try to figure out how to do this. Okay, anyway, but now we're ready to write conservation of energy. Okay, so let's say the potential is 0. By definition, you can always set a potential to be 0. Then you got to decide what is the potential at the other location. Is it positive? Is it negative? Whatever. I'm going to call the plate potential 0. U equals 0 at the plate. So I shot the electron from the plate. So I have kinetic energy. So somebody had already written it. Let me just rewrite it. I think what they wrote is, Emma wrote it with just df, but the rest of it was fine. So 1v0 squared. So that's the kinetic energy initial. So the total kinetic energy is this, right? Now plus 0, because I'm calling the potential energy 0. Yeah, you can solve this without okay, let's solve it and then see if I answer your question. So I'm only using V0. V0 is a given. I have to give you V0, otherwise you wouldn't know how high it will climb. I actually have to give you V0 and I also have to give you the angle. The angle also. For different angles is because different elevations. So equals. Now, what is the kinetic energy at the top? So the temptation again is to say, the 45 would have to be in the problem, right? I could leave it in terms of theta, but then I have to tell you what theta is. So it says 1/2. Okay, so the temptation here is the temptations you've had in writing replies. The temptation is to say that at the top the kinetic energy is 0. That's what you usually say. That's only true if you're shooting straight up, because in that case, what the kinetic energy at the top, we already decided, was V0 cosine of the angle. If you make the angle 90, cosine of the angle is 0, then there is no kinetic energy at the top. So if you shoot it straight up, it goes straight up, then it stops, and then comes back down. Only in that case, the kinetic energy at the top is 0. But in general, it's not 0. And you need to square this, and then you need to square that. And since I chose 45, then there would be a 45. 1/2 mv squared. V0 at the top, the Vx at the top is V0 cosine 45. That never changes. No. Oh, I see. Well, you're doing something already. Let's get there. Let's get there. Well, no, not really what you're writing, because you need to square it. So that obviously you can't. But we're going to get to the expression you're trying to get to, Isaias. We can rewrite this in a second. I'll do what you want. But you have to square it. If you don't square it, then it's not going to. The units won't work out for you. But we're going to get to the form you want in a second. Okay, so we have 1/2 mv squared. What I'm doing is fine. You're following the procedure, okay? So it's the initial kinetic energy, the kinetic energy at the top, plus, now you have to decide, is it plus or is it minus? Okay, so the answer to our question is like this. Is the kinetic energy increasing or decreasing? If the kinetic energy is decreasing, then the potential should be positive. If the kinetic energy is increasing, then the potential should be negative. So which one is it? Should I write a plus or a minus? So I do QE times H, the potential at the top. Should this be a plus or a negative? This thing here. The whole thing should be a plus. Correct, as Roy just said. It should be a plus. Obviously, if it's going to go up, it's slowing down as it goes up. Still moving in the horizontal direction, the speed is not changing, but it's slowing down. The kinetic energy is decreasing. You can't get rid of kinetic energy without putting it into potential energy. So if the kinetic energy is decreasing, the potential energy should be increasing. So notice what's going to happen here. And no, this is important. Otherwise, again, I'm trying to tell you how to figure out the plus sign or the minus sign without thinking about all the signs and the formulas. It's much better to do it that way, in my opinion. So the problem is the way we wrote this, which is fine, there's no problem with it, but we're going to end up saying QE is negative. And then we're going to get confused because we're going to say QE negative, so therefore this is negative then. And then we have the wrong sign in there all of a sudden. Okay, so you can't do that. You have to decide from the physics what the sign of the term should be. So since if the kinetic energy is decreasing, the potential energy must increase. End of story. Okay, that takes care of the signs. So whatever term, so I have more kinetic energy here on the left. So therefore, I have to have more potential on the right. Since I call this zero, the thing on the right has to be positive, end of story. The potential on the right side has to be positive. So let me write it for that reason. It's a lot easier and clearer to write it like this. So this is why I like to write this around the charge. Because otherwise you're going to end up putting the sign in there. Now remember that this is a positive plate. So the electric field points up, away from the positive plate. So the electric field is positive, points up in the y direction, which we call always positive. So there's no way to put a negative sign from the electric field, but unless you do this to the charge, you're going to end up putting a negative because of the charge, and it's the wrong sign. That wouldn't work if you put a negative, because then it would be less potential at the top, and that doesn't make any sense. It's not physically plausible. Okay? Hopefully you got that point. Please trust me that that's better to do it that way. It's a very simple rule. There's no exception to this rule. There's never any situation. You're always conserving energy. So if the kinetic energy is decreasing, the potential energy must increase. End of story. It doesn't matter which situation, what the charges are, whatever. If the kinetic energy is decreasing, the potential energy is increasing, and vice versa. If the kinetic energy is increasing, the potential then is decreasing. So for sure, I guarantee you, you need a plus sign you need this to be positive for this to work out. Okay. Please think of it that way. It will make the signs easier. There will be a lot fewer confusions of putting negative signs. Otherwise, you have to start to figure out where is the electric field, where is the charge, where is, and then you could just start saying, oh, start putting different signs for different things. Okay, so that's it. So now I'm gonna do what Isaias wanted to do. He wanted to write it in terms of sign. So how would I do that? Well, it's pretty easy, actually. I'm going to get the same expression he was aiming for. He just missed the squared part. But if I move them, so I could rewrite this way. And then I could have a 1. And then I would have a minus cosine square of 45 equals QE E times H. Right? I just move this term to the other side, and I factor out this term. Okay. Well, there's always a rule that says sine square of an angle theta plus cosine square of an angle theta equals to 1. That's always true. That's a you know, a general expression. So therefore, I can rewrite this as the sine, which is what Isaias wanted to do. Just using this general expression, I can show that sine square. Well, I mean, let me just do it. So therefore, 1 minus cosine squared of 45 degrees, I can just write 1/2 mv0 squared sine squared of 45 equals QE EH. Again, don't worry about the sign, otherwise it doesn't make it. The thing on the left is positive. You can't make the thing on the right negative. That doesn't make any sense. Okay, Isaias, I know you arrived at the right formula, but your thinking is not correct. You have to think of it this way. And let me say why again. When you're doing energy conservation, there is no X and Y components. Energy is not a vector. So you cannot do conservation of energy in the Y direction independently from conservation of energy in the X direction. There is one conservation of energy. There's initial energy, there is final energy. And then you can rewrite that expression however you want. Now, if in this case it happened to work out for you, good for you, but that's not, it will get you in trouble in some other situation. In this situation, maybe it wouldn't get you in trouble, but in other situations it would. No, you cannot do conservation of energy independent in the Y direction. What you're thinking is, again, if you have a vector, I know what you're thinking. You're thinking, if you have a vector, I have to balance both sides. So I could do balance in the Y direction, like force balance in the Y direction, then force balance in the X direction. And they both must be true because it has to balance in every direction. And then I have equilibrium, say. Yeah, you could do that with forces because forces are vectors. But this is not, energy is not a vector, so you don't do energy balance in the Y direction, energy balance in the X direction. Okay, anyway, let me, we don't have a lot of time, but we have enough time to just show you something very quickly, just how you would set it up, just for completeness. What I wanted to just show you, and I made sure to do in advance so I don't mess it up right here, doing it very fast. So I have it in front of me. So I'll just tell you, let me do the kinematic thing. I'll go pretty fast. I have it in front of me. I don't have a lot of time, but I want to give it to you. Kinematic approach. So I'm going to write it to the same thing. Just to show you that you get the same exact thing. It's not even, you're going to get the same, precisely the same thing if you use this kinematic approach. So again, we're trying to calculate what would be the elevation of something. You can write the formulas in full fashion like you would, like I did the first time. Let me not do that. Let me just, go right to the formulas. So remember, in the X direction, there is no acceleration. AX equals 0. In the Y direction, the acceleration, we already know what it is the force, which is QE divided by M. And if I want, it's in the negative Y direction, so I could just do what I did above, which is put a minus and then put absolute value, just not to double count that minus sign. So meaning the magnitude and then the minus. So this thing is definitely pointing down. The acceleration is pointing down. That's why the electron starts to turn and starts going down. Okay, so you definitely need that. Okay, so then I could just say, okay, let me just, again, I'm gonna go fast. Sorry about that, but I only have 4 minutes. So I wanna write down the formulas here. So you would have X. What is the X component of the electron? Well, that would be V0X times time, which is V0 cosine theta. In this case, theta is 45. Let me write 45 to make clear what that theta is. V0 45 times time. That's the X component of the electron. Now the Y component of the electron would be V0Y, which is V0, instead of calling it that, let me just call it this. V0 sine of the angle, that's V0y, times time. That's the initial speed in the y direction, V0 sine of 45, plus the acceleration, but let me just already put the right formula. So it's a minus 1/2, and then it would be QE E over ME times T squared. These are the kinematic equations for the position of the electron at any time t after you fire it. Okay, now, great. So what is the condition that it reaches the top? Emma gave it above. The condition that it reaches the top is that Vy at the top is 0. So we need an expression for Vy. And then the condition that at the top is Vy equals 0. And that's the time, then you solve for the time using Vy equals 0. That's when it reaches the top. Okay, so we have to have the expression for Vy. So how did Vy go? Well, it went V0, the initial, sine of 45. And then you have minus, again, it's 8 AYT. So that would be minus QE E over M E for the electron times time. That's the Vy. Okay? So I'm solving for Vy equals 0. That's what I'm solving for. I'm solving for the time at which it reaches the top. No, for y this time is t, Rohit, right? For the position is t squared over here. But this is the velocity. Right? So how does, let me write it down. The velocity goes Vy equals V0y plus AY times time for the velocity. The t squared part is when it's for position. We wrote those equations last time, but yeah, okay. The 1/2 t squared corresponds to the x and the y components. The velocity component just has one factor of t, not t squared. Okay, so solving for Vy equal to 0, that gives me time. So I want to get all the way to the bottom. So give me 2 more minutes and I'll get you the same formula we got above by using this approach. So you see it's the same thing. Okay, so in 2 minutes I should get there. And then we can, if you're still confused about something, we can go over this again, but let me just finish up here. So if I do this Vy equals 0, whoops, and stick it in there, then I can solve for time. So this is the time I get from that. T equals ME V0 sine of 45 divided by QE. And again, I keep putting the magnitude here to say, don't worry about the sign. You already took care of the sign. Times C. This is the time at which the electron reaches the maximum spot, because that's the time at which Vy equals 0. Okay, now I take this time and I stick it in the y equation. I take this time and I stick it in there and also in there. Okay, because then I found h, the elevation at that time. So let me do that. So h equals, and I have the formula in front of me. I'm gonna go fast. I'll write you what comes out. So it's V0 sine of 45. And now times time. So the time we just calculated above. So let me write down what that is. V0 sine of 45 divided by QE times the electric field minus 1/2. And then now it's AY, and AY is QE E divided ME times time squared, which is this thing here I just wrote above, but squared. ME V0 sine of 45, and then divided by QE E, and then I have to square this whole thing because it's t squared for the second term. Okay, hopefully you can see my handwriting. If somebody didn't get my handwriting and want to stay a little longer, I can clear up my handwriting. But right now, so actually you can rewrite this so there is when you multiply this thing by that thing, it comes out to, of course, it has to come up to the same power of that, but there is a minus 1/2. So this is a 1 here. So 1 minus 1/2 equals 1/2. So this, the whole thing I wrote here becomes this: 1/2 V0 sine of 45 times ME V0 sine of 45 divided by QE times E. That's it. So that's the same thing as above. Okay, so that agrees with what we wrote up here. Because I'm just moving this thing over to that side. That's the same thing. Okay, anyway, yeah, I did go a little fast, but it's because I was running out of time. I don't like to go over time. But anyway, it comes out, you can do it yourselves, but it comes out to exactly the same expression. It's the exact same thing. So it doesn't matter whether you solve kinematic equations or you do energy conservation. Of course, for this problem, energy conservation goes quicker. Of course, you can see that I did more stuff here at the bottom. But that's it. Okay, do you have any questions? Class is over. So do you have any questions? If you do, that's fine. We can, I don't know exactly what I'm going to ask in the exam, but it will be something of this kind, yes. That you shoot an electron and ask questions about it. How high does it go? What is the speed when it hits the plate? Whatever. How far does it travel? I could ask as well. Like horizontally, how high does it go?